Today, she will talk about decoding the cosmos with gravitational waves. We are very much looking forward to your talk. The stage is yours, please.
Thank you very much for the kind introduction. Let me begin by apologizing to most of the people I met today because I know I was late in every meeting, and that's because I really enjoyed the interactions with all the faculty members and the community. So thank you very much for that. As Stephen said, I'll be talking about decoding the cosmos with gravitational waves. Let me start referring to this. Sorry, it's running out slower. Okay, it's okay. Okay. So let me start by a reference to a sci-fi movie, The Arrival, where we saw the humans decoding the language of the aliens, and the aliens were sending out the symbols called logograms, which basically embed the whole information of a phrase or a word within that symbol, instead of a sound or a syllable like our normal languages do. And by identifying these symbols, the humans were finally able to understand the message that the aliens were trying to send to us. Physics is the language of the universe. With each new discovery, we're getting a new logogram, and as we understand the relationship between these different logograms, the common patterns that emerge, we will be able to understand how it all started and maybe even where we are headed. Just a disclaimer, I'm not saying that these logograms are being sent to us by intelligent life form. It's just an analogy. So what have we learned so far? We know that our universe is expanding, and we know that the expansion is accelerating. We think that this is powered by something called dark energy, but we don't know very much about it. All we know is that it comprises nearly 68% of the energy content of our universe. And it is represented often by lambda, which is called the cosmological constant, as you see over here. And that's more or less what we have learned so far about this. We also know that the visible matter that we see in our universe cannot account for the gravitational effects that we see at the scale of the galaxies or even larger structures than that. We think that this is something that can be explained by something called dark matter. Once again, we don't know very much about dark matter. What we do know is that it comprises about 27% of the energy content of the universe. So that leaves about 5% of the visible matter. So everything that we know, everything that we see, all the galaxies, everything, it's just 5% of the energy content of the universe. Based on galaxy surveys of large-scale structures, we know that all of this visible matter resides in these filament-like structures, and together with the dark matter that has helped in shaping the structure of these filaments, what we have is some sort of a web-like structure called a cosmic web, based on numerical simulations that can reproduce this cosmic web that we see observationally. We know that the dark matter has to fold. And so this forms our current best guess of the universe, which is the lambda CDM model. The lambda stands for, as I mentioned before, the cosmological constant, and CDM stands for cold dark matter. Within this model, we know that it all started with the Big Bang, and then that was followed by an era of rapid expansion, an inflationary era. Then, as the universe started to cool down, photons were able to travel freely. And that radiation is something that we are still able to detect. It's called the relic radiation, or the cosmic microwave background that's from around 380,000 years after the Big Bang. That was followed by an era of atoms and molecules forming and matter coming together, finally leading up to the formation of the first stars. We still haven't seen the first stars. So the first observation we have from the universe is from this era of CMB. And this is the earliest observation of our universe that we have. So based on the CMB, that's kind of like the most useful picture of our universe that we have. Then there is no observation again. Then again, the first stars started forming, and as I said before, we still haven't seen the first stars. And then that was followed by billions of years of more structure formation, galaxies, large galactic structures, and all of these things we have seen in galactic surface. So we know the existence of these large-scale structures, but we don't know exactly how they are formed yet, because as I said, cosmic expansion and as well as dark matter, all of these things have gone into the structures being formed the way as we see it today. So as you can see that our understanding of the universe is interspersed with observations and also unverified theories. As we are able to see more things, we get closer to verifying some of these theories. And with the currently operating different telescopes and observatories, and the future upcoming ones, there is a great potential of uncovering more of this information as we keep going along. To name a few, the JWST, which as most of you may know that is currently operational, we have seen galaxies at larger redshifts than ever before, so from very early on, and we hope to see the first stars with JWST. This year already, the Vera Rubin Observatory is going to soon start taking data. With this, we expect to see the most accurate map of the universe, of the large-scale structure in the cosmic grid, therefore. And then coming up in a few years' time is the Rubin telescope, which is going to track the expansion history of our universe to a very high accuracy. This once again will let us know more about the cosmic expansion and also the dark energy. I should mention over here that what I've said so far and the cosmological timeline that I showed in the previous slides is constructed largely based on electromagnetic observatories and electromagnetic astronomy. But now we have this new kid in the block. In fact, this year marks the decade of gravitational wave astronomy. The first detection happened in 2015, and since then, this marks the decade of that event. With the observatories the gravitational wave observatories that have been operational up until now, we have seen many black hole binaries and a couple of other binaries, and I'll talk a lot about that in the slides to come. In the upcoming observatories in this regard, we have Cosmic Explorer, which is supposed to be much more sensitive than the currently operational gravitational wave observatories. And we are expected to see much further away, much higher redshift, and therefore possibly black hole binaries that are formed in these early galaxies that I mentioned earlier that JWST. And then later on in another decade or so, there's the upcoming LISA space mission, which will see the merger of the supermassive black hole that is posted at the center of all galaxies, as we currently believe it is so. And as we see the merger of these massive black holes, they also help us understand our galactic mergers. So overall, this will help to construct the map of the universe at a higher precision. But you might ask that if we were able to construct the cosmological timeline based on EM observatories, then why does GW astronomy help us further, or how does it exactly help us further? And this is what I'll talk about. Before that, let me quickly introduce what gravitational waves are. General relativity is still considered the best description of gravity. In this theory, gravity is described as curvature of space-time. So the more mass you have, the more curved space-time around it is. Coordinations on the space-time travel out like ripples on the surface of water. So ripples of the space-time are what gravitational waves are. And when these ripples travel all the way out to us, they compress and stretch the detectors that we have on Earth. The gravitational wave detectors are usually these interferometers, which are two arms at 90 degrees from each other, and two light beams are sent along each of these arms. They reflect back from a mirror on the other end of the arm, come back again, and when they recombine, if the lengths of the two arms are exactly the same, the lights recombine or interfere constructively, and therefore you do not see any phase difference or any difference in the patterns that they are producing. As the gravitational waves passes through the detector, if you assume it's passing directly perpendicular to the plane that consists the detector, the arms alternatively contract and expand. So as you can imagine, that the length traveled by each beam across the two arms will differ. And now that the lengths are differing, the light that is reflected back from the mirrors, they start showing a phase difference. And because of this phase difference, you do not see the same interference pattern as you would see if the arms were at the same length. And then you conclude that a disturbance in space-time has passed through the detector. But what causes these kind of disturbances? So a gravitational wave is constituted by a time-varying mass-dipole moment. And a special class of this are asymmetric perturbations onto the surface of a gravitating object. Now that's a lot of jargon. Let me try to use some visual illustration to explain what I mean by that. Imagine if you have a cylinder that is rotating about an axis that's passing through the center of the cylinder along the longitudinal axis, along the axis that passes through the bottom of the cylinder. And let's say the period of rotation is capital T seconds. As the cylinder rotates into the plane, it basically leaves a shape of it on the plane, much like the coyote would when it runs through a wall. So now if we track this shape on the plane at different intervals of time, what does that look like? After a quarter rotation, as the cylinder rotates into the plane, we see a rectangle, essentially a rectangular cross section. Another quarter rotation later, we still see a rectangle. Another quarter later, rectangle. And finally, at the end of the full rotation, we still see a rectangle. So this we conclude is there is no time variation to the mass particle moment. But what happens if we turn the cylinder on its head? Now the rotation is about the axis that's transverse to the length of the cylinder. So basically the rotation looks like this now. A quarter rotation later, the cylinder length is oriented along the y-axis entirely. So if you look at the shape that it's carving on the plane, you see a semicircle. Another quarter of rotation later, it's back on the same orientation, but this time it's just the opposite orientation as before. You see a rectangle again. Another quarter later, it has gone back along the y-axis, you see a semicircle. And finally, at the end of the full rotation, you see a rectangle. This constitutes a time-varying mass particle moment. Let's do one last example. What about a big rotating black hole? A rotating black hole is still a spherical distribution. As it rotates into the plane, we play the same game again. We see a semicircle at t over 4, semicircle t over 2, semicircle at 3t over 4, and finally, even after a full rotation, you still see a semicircle. Once again, there is no time variation to the mass particle moment. As I said before, a time-varying mass particle moment is what constitutes a gravitational wave. So by now, maybe intuitively, I've already guessed that the mass particle moment is basically the mass distribution. So it's not the total mass, it's exactly how it is distributed. And if that distribution changes over time, only then will you have gravitational waves. As I said before, a special class is when you have an asymmetric perturbation onto the surface. So again, let's talk about black hole. Or if you've heard about event horizon, the special surface on which nothing can come back out of the black hole. So if you have an asymmetric perturbation onto the black hole, it disturbs the surface of the black hole, much like if you had a bubble of fluid entirely, a spherical bubble, and if you drop something on the bubble surface, the fluid kind of slosh around till it comes back to its natural relaxed state. Or you can compare with a more solid object like a bell. If you strike a bell, it rings and tries to get rid of all this extra perturbation by sound, by emitting sound, just so that it can relax back to its normal state. So this is called a ring down, which again I'll mention later on. So if you have asymmetric perturbation, it will cause this. And it's important to remember the asymmetric part of it, because if you have a spherical shell of matter falling into a black hole from all directions in this very asymmetric way, you do not get any gravitational waves. On the other side, if you have Cooper falling into it, you will get gravitational waves. What about an asymmetric collapse of a black hole into a neutron star or a black hole? Sorry, asymmetric star collapsing into a black hole. That will also lead to gravitational waves. What about a black hole devouring a star? Well, usually when it devours a star, it kind of tears it apart and then falls, the matter falls into the black hole from all sorts of directions. It would be very unlikely that the matter would fall in a spherical symmetrical way. So you would get gravitational waves in that case as well. But what about a star that has a large asymmetry in the mass distribution? Would that produce gravitational waves? Well, if it is non-rotating, as is the case over here, as I said, in that case, you do not have a time-varying mass particle moment, and therefore, in that case, again, you do not have gravitational waves. So as you can see from this chart over here, there are multiple situations where you would have gravitational waves coming from all kinds of astrophysical events. Another case that I did not mention here, that's because I will talk in great details about that later on, is the coalescence of binary stars or any kind of binary objects that also leads to gravitational waves. So the gravitational wave sky is pretty bright, but can we detect it? What are the chances of detecting it? Well, actually, with gravitational waves, you have certain advantages in terms of detections. One is that the signal strength falls off as 1 over r as opposed to electromagnetic waves, where the signal strength falls off as 1 over r squared. So you win a little by the signal strength being strong enough to a further distance. The other reason why it's useful is because nothing is really opaque to gravitational waves. So in case of electromagnetic waves, if you have a solid enough obstruction between you and the source, you will not see it. But with gravitational waves, no matter what you have, it will pass through it, stretching it on its way, but at the same time, making its way all the way to your detector. A third reason why gravitational waves are advantageous is because if you want to build a detector, your detector is sensitive to the whole sky. So unlike electromagnetic astronomy, if you're not pointing to the right part of the sky, you would miss the source. In this case, you don't have to point your detector to any direction. As long as the gravitational wave is passing through Earth, we will detect it. But then it also has some weaknesses, the main of which being that gravitational waves are typically very, very weak. The quadruple formula is an approximation of Einstein's GR. Einstein's GR is the general relativity is what you have to use to calculate gravitational wave typically. But you can use an approximation to get order of magnitude of the strength of the signal. And from there, if you look at this equation right over here, the Iij, this part basically gives the estimate of the mass particle moment variation. And you can imagine that for astrophysical objects, that number will be pretty large, right? Because you have tons and tons of or massively large masses of solar matter or stellar matter that sometimes moving at really high velocities close to the speed of light. So while this number can be very large, you also have to look at this prefactor. The prefactor is 10 to the power of minus 43 over r. And r, as you can imagine, for astrophysical sources is also very large because r is the distance to the source. So that just makes matters worse. So therefore, the signals are typically very weak, and you need to have some source which is extremely massive and moving at extremely high velocities to be able to get a signal that's detected on our detectors. And the other weakness is also, as I said, one of the strengths. It is sensitive to the whole sky. So which means while it is sensitive to all the signals in all directions, it is also sensitive to all of the noise sources from all directions and also all sources at the same time, which makes understanding the noise budgeting of the detector and detector characterization overall a very important part of gravitational wave astronomy. To give you a visual representation, this left panel is what pure noise looks like, and this right panel is what noise with a signal looks like. And you can tell that by looking at them, you can't tell them apart. So there's no way that you would know by looking at this that, oh, this is a gravitational wave. EM astronomy typically involves looking for a bright patch in a dark sky. There's a lot of noise involved, and there's a lot of data analysis challenges in EM looking there. But let's say if you have a very bright event happening in the sky, you couldn't even see it by naked eye without even needing a telescope. That's never going to happen with gravitational waves, because even if you have a very loud event that's hidden in this kind of data, you would always need to know something about the time-frequency relationship of the source in order to determine that it has an astrophysical origin and it's not some kind of random strange thing happening in the detector, as Marco can tell you about. Therefore, understanding the time-frequency relationship for gravitational waves is a very important part, and this is what source modeling is. One of the gravitational wave sources that has been modeled and that are very well understood are compact banded coalescences. An obvious reason for that is this is the first source and till now the only source that has been detected in our detectors. The plot that I show over here is from the first event that has been detected, which is known as TW1514. It was the merger of two black holes of mass 36 solar masses and 29 solar masses. Compact banded coalescence is typically characterized by an inspiral region where the objects are quite far away from each other, such that you can get away by not solving the fully relativistic equations, because this is known as a weak field limit, where the objects are moving slow compared to when they get much closer. And also, the curvature of each of the objects do not affect the motion of the other object. So you can kind of get away by assuming Newtonian gravity and not having to account for the curvature to that extent. As the objects orbit each other, they get closer and closer, and finally that leads up to a merger when the two objects become one. And this final object that is formed, this rings down because as the objects are approaching each other not in a spherical symmetric way, so when they merge, that leads to an asymmetric perturbation on the surface of the final object that is formed. And as I told you before, that leads to gravitational wave emission. So this whole process of spiral merger and ring down is accompanied by gravitational waves. Now, normally, as I said before, to calculate the gravitational wave strength, you would want to solve the full relativistic equation of Einstein's GR. But there's a challenge to it. It's a highly nonlinear system of equations, so there are no closed form solutions that you can find for generic systems. So you'd use a computer to solve those equations. And this is the field of numerical reliability. Now, the challenge of that is that these simulations are extremely expensive. To give you an idea, the easiest ones run in 10 days, and the complicated ones can take up to 3 months or even longer. And even with that, you get to simulate only the last 10 to 15 orbits of the simulation. But the last 10 to 15 orbits is not enough to actually detect the full signal and get the most astrophysics out of it. So what is typically done, if you look at this plot over here, on the y-axis, I show the separation, so how far the objects are from each other. And when the objects are really far away, so really high up along the y-axis, you can get away by assuming, as I said, the weak field limit, so you can ignore curvature, and you can use some approximations like post-Newtonian theory. That by using that, you can calculate the gravitational radiation in that region. But then as the object starts getting closer and closer, you can imagine that the binary is basically moving down this direction, and at some point it enters into the NR region, and you cannot get away by making any approximation. So there you have to use full relativistic simulations. And then in this intermediate region, you have to find physically motivated ways of smoothly transitioning from one to the other. Once you have done that, you have a set of data. Now you need to produce analytical fits for this entire region that will describe the waveform, characterized by different parameters that describe the system, like masses or other parameters that you might want to put into that. So this is how the phenomenological waveform family came to be. It's known as phenom in short, which is short for pathological. The waveform that I show over here, phenom D, was the waveform that was used for detecting the first signal, as I mentioned before. And then there were several other iterations that came along over the years. Now, you might wonder that if phenom D was already good enough for detecting a gravitational wave grid, then why do we bother with further iterations of it? And there's a reason for this. As you improve the waveform, the precision and the accuracy with which you are able to recover the source parameters, which again I said are the masses, and also the spins of the black hole, that also gets better. If you have better estimates for the spins of the black hole, that feeds into our knowledge of black hole populations. What that means is that are these black holes born in isolation as binary stars and then they finally evolve together? Or are these formed in dense stellar environments through many more interactions or through any kind of other environmental effects? And this is something that we really want to understand better to understand how black hole formation has evolved over the time. When you have better estimate of the black hole masses, that gives you an idea about the origin of the black hole. So normally we expect that stellar black holes are born by collapse of a star, but that typically has a certain mass range beyond which we would expect to see black holes of stellar origin. If you see black holes in that mass range, then there are different channels through which it may have formed. It may have been that the black hole was formed, and then it started accreting material around it. But then for that, there has to be material around it. So it has to be formed into some kind of an environment already. With better distance measurement, you get an independent measure of the cosmic expansion. The other measure you have are from electromagnetic astronomy. The measure that you can get from gravitational waves is an independent measurement completely. And therefore, this would help to improve the constraints on the cosmic expansion measurement. And finally, CDC waveforms also feed into testing gravity, because as I said, the entire model is being built assuming that GR is the criteria. So if you make a very accurate model of the gravitational wave signal, then when you remove that signal from your data, if you have coherent power left in your data, if you have enough strength of signal still left in your data, then that's a signal that there's probably more to it than just a binary black hole evolving in GR as the criteria of gravity. And I'll spend a little more time on two of these examples to tell you why it is important to keep improving the waveforms that are used in our analysis. Waveform improvements are always driven by measurability and a certain detector sensitivity. And that always feeds into what is prioritized to be modeled next. So the first example I talk about are black hole spins. As I said, if a black hole may have either evolved in complete isolation or it may have evolved in an environment. If it is evolving in isolation, we expect the spins of the black holes to align with the direction of the orbital momentum. But if it is evolving in an environment by some dynamical capture or the presence of a third object in the vicinity of it, that may actually cause those kind of effects will produce an isotropic distribution of spins. There's no reason why the spins should be aligned with the orbital momentum. The spins can be directed in any direction. And there's a distinct difference between these two kind of systems. These are known as aligned spin systems, where the motion of the binary throughout the process is confined in a fixed orbital plane. So the only motion you see of the binary is that they're inspiring towards each other, finally merging. But precessing systems, when you have significant amount of spin misalignment with the orbital momentum, causes the plane of the binary to precess. So if you look at the motion, it would look very strange. You would not even be able to tell where the orbital plane is. Now, the precession imprints are actually left on the waveform. So one of those imprints is basically a asymmetric emission above and below the plane. So for precessing systems, the emission that you would see above the orbital plane and below are not the same. But for aligned spin system, the emission above and below the plane are symmetric. The first model that were made, the phenol B model that I mentioned earlier, that has this symmetric emission above and below the plane because that model was for aligned spin systems. For the processing systems, or waveforms for processing systems were built upon these aligned spin system waveforms, and therefore they inherited this symmetry property that does not hold true for processing systems. The reason why this was left out, or this asymmetry was not taken into consideration, is because it was understood to be a small effect. And as I said, waveform modeling improvements, because these are expensive, you still have to produce an simulations, etc., because these are expensive adventures, so to speak. So improvements in waveform modeling is always motivated by measurability of an effect at a certain detector sensitivity. Yeah, so all the models, all the framework models up until the current observing round in the gravitational detectors did not include the asymmetry. I have recently made a model of this, and I have included this model into the current phenol model that is going to be used for the next observing round or the ongoing observing round for the catalog of this. And the reason why we did that is because while this is a very small effect, we also understand that it is associated with an important physical effect. When a gun is shot, we know that there is a gun recoil, which is basically as the bullet shoots out, it's carrying a linear momentum along with it. And therefore, for conservation of that linear momentum, the gun fires backwards, and this is what causes the moment to fall over. We know that gravitational waves also carry energy and linear momentum. As the black holes are going through the spiral, the whole time it's releasing gravitational waves and energy and linear momentum through it. Finally, at merger, a significant amount of gravitational wave is released. And at that time, if the emission is not symmetric, in that case, the asymmetric emission has to be compensated for by the merger element recoiling in the direction that accounts for the asymmetry. And this asymmetry that I mentioned before is exactly what is responsible for the recoil of the final remnant black hole. And in fact, a student of mine looked at this. So he tried to produce the different recoil velocities that the final black hole would have as a function of the strength of the asymmetry, which is what is shown on the x-axis, and the y-axis shows the velocity that the final black hole can have depending on it. And he found this rich structure of the peak velocities based on the strength of the asymmetry with the model that I made for asymmetry, and that is what is the current model of the newest round. And then he also calculated the velocities for other Fresnel models that were there in the past, and all of them basically give you zero. So this was verified that unless you have this asymmetry into the waveform model, you are not going to find any peak velocities associated with the waveforms. Another inspection that we did with this new model again was about the spin measurements. As I said, that spin misalignment causes this precessional effects. The precessional effect imprints on the waveforms, and therefore the ability to measure the spins properly gets better as you keep adding these precessional effects. So the plots I show over here are called spin disk plots. Each of these half disks represents the spin of the primary and the secondary. So this is for the primary, which is the larger black hole, and this is the secondary, which is the smaller black hole. And the one on the left corresponds to the model that has the asymmetry, and one on the right corresponds to the model that did not have the asymmetry. So if you look at this, the color over here shows the probability distribution of the spins that you recover from data analysis. And the radius of this semicircle represents the magnitude of the dimensionless spin of the black hole. And the angle that you see in this disk represents the misalignment with the orbital angular momentum. So 0 degree would correspond to completely aligned spins, and 180 would correspond to completely anti-aligned spins. And if you look at this, the pink cross that you see, those are the true values with which the signal was produced. And then after data analysis, we found that the highest probability, which is this darkest region, is very close to the true value for both the primary and the secondary, the larger and the smaller values. With the model that did not have the asymmetry, this is the highest probability region, and the white region is where the probability is entirely zero based on the model. And if you look at these two plots, for both the primary and the secondary, this model does not recover the swing values at all. So unless you have this asymmetry into the waveform, you are probably going to recover really wrong values of swing. And especially worrying is that in this case, you recover completely aligned swing, while the system is actually misaligned. So therefore, you would have a completely wrong notion of whether the binary was born in isolation or whether it was born in some kind of environment.
So can you say what kind of system do you assume?
The previous one?
Yeah.
So, sorry. So this one is a mass ratio 1, so equal mass. Yeah, equal mass system. Equal mass system are the systems where the asymmetry is strongest. So with that, I would like to move on to another example of how improving compact binary coalescence waveforms can help us understand more about the universe. And we'll shift here to a slightly different kind of source over here. Dark matter is very, from our understanding, very sparsely distributed in halos. Normally, these kind of densities, we don't expect it to be significant source of gravitational waves. But there are some processes by which local overdensities may occur near a black hole. So if you have a black hole and some dark matter near it, then through a process of superradiance, if the black hole is rotating, the dark matter field can grow and form these cloud-like structures around this black hole. Note that here we are only talking about a single black hole, not a binary. So this would happen to any black hole as long as there is some amount of dark matter around it. The cloud grows at the expense of the black hole losing its rotational energy, so the black hole spins down and the cloud gets larger and larger. So you have this sort of lobe-like structure that forms around the black hole, which are not symmetric, not spherical symmetric, and they are rotating. So now you have a time-varying mass particle moment. And therefore, these turn into sources of gravitational waves. What we found was that these gravitational waves could be detected by current detectors that we have, or even the future detectors, depending on how far they are away from us. If they're quite far away, then it's harder to detect them. But if they're close by, these sources produce a detectable signal at the gravitational wave detectors. But more interestingly, what happens is that the frequency at which these signals are emitted is entirely determined by the mass of the dark matter component candidate that you're looking at. So which means that irrespective of the mass of the black hole, all black holes in the universe will produce the signal at the exact same frequency. Because if you assume that there's only one dark matter candidate in the universe, it has the same mass, and therefore when it goes through the superradiance process, it emits gravitational waves at the same frequency. There's one caveat here. While it emits at the same frequency, as you look at the signal generated by a population of black holes spread out over the entire universe, they are at different distances from us, right? So therefore, the signal that is much farther away would be redshifted somewhat. So instead of, if you look at the combined signal of all these unresolved superradiant clouds, what that means is that all the black holes that have undergone this process and are emitting gravitational waves that are too far away to be detected, but they will all combine together to form an unresolvable background, almost like a noise for other sources. And then, if you look at the power at that particular frequency, you should be able to find that signal. Now, you have to account for this redshift that I mentioned earlier because you're using a population which is spread out all over the universe. So instead of looking at a particular frequency, you look at a spread of about a decade in frequency. And it turns out that this signal is also something that could be detectable by current or future detectors. The black bucket-like lines that you see are the sensitivity, detector sensitivity curves. And this signals that you see are basically solid lines at different colors. The different colors represent different masses of the dark matter candidate. The reason why we have different masses over here is because we wanted to see at what masses are these detectable. So we are able to probe a certain mass range for the dark matter candidate because we don't know what the exact mass of the dark matter candidate is. Now, the reason why this is important is there's a plethora of particle physics experiments that are looking for dark matter candidates that fit the budget exactly of something that would produce a cloud like this. So you can see the whole mass range that they are scanning through this wide range of experiments, very expensive experiments. So if we are able to see a signal through gravitational waves, then that immediately collapses all these efforts and streamlines all these efforts in that short mass range. And therefore, it's very important to look at this kind of a signal in gravitational wave detectors. This also highlights once again the importance of observing the same event or same kind of things through multiple messengers. The gravitational researches that are done, there has been 3 observing runs by the LIGO, Virgo, Power collaboration, has already looked for these signals, and unfortunately we haven't found anything yet. Not finding a signal helps us put constraints on the mass, possible mass of the dark matter candidates, of course. But there's another different way for looking for these signals. A dark matter over density like this could happen near one of the components in a binary or both of the components in a binary. If a dark matter candidate exists, there's no reason for either of these black holes to not undergo this process. So if such a cloud happens, we are routinely detecting compact binding coalescence. We expect a cloud like that to somehow imprint on the compact binding coalescence signal. But the thing is that these clouds are formed very close to the black hole. So we cannot do any kind of analytical approximations to get the true imprint of it on the CDC signal. So if we numerically simulate those spacetimes and regions of extreme gravity very close to these black holes, we can find how this imprints on the signal, and then by making accurate CDC waveforms in GR, understanding the imprint of the dark matter cloud in GR, we are able to get more information from our individual events and find out if there is a possibility of such a cloud existing. So in a way, CDCs are the newest logograms that we have. So based on over 100 events that have been detected in the last 3 observing rounds and more to come with the current run, where do we stand now? Well, we are seeing black holes smaller than what we expected to see. We have seen black holes much larger than what we ever expected to see. We have seen black holes that are consistently of low spins. We expect to see higher spin in the black holes, but somehow we haven't seen higher spin black holes that much yet. And whatever we have seen, based on all the tests that have been run, everything has been found to be resolutely consistent with GR. So we haven't seen any deviations from GR yet. So I asked ChatGPT that with Cosmic Explorer coming along, what does the future look like? And this strange, preposterous image was what it generated. So I started looking at scientific studies again. I suppose this means that scientists will keep their jobs for a little longer. If you look at this plot right here, this was a study that was done for Cosmic Explorer. On the y-axis shows the certainty with which a science goal can be achieved, and the x-axis shows the network or the configuration of the instrument that is supposed to be used. So let's just ignore the x-axis for now. On the y-axis, if you look at this, we expect to see, as I said, the first black hole model, as in the mergers of black holes that were produced from the first stars. We expect to have very precise measurements of the distances. We expect to learn lots more about neutron stars and the nuclear physics of the neutron stars. Neutron stars are not something I've spoken about due to constraints in time. We will also understand the history of compact objects because we see compact object mergers at different redshifts, so that helps us understand the evolution history of these objects. And we will have much more stringent tests of strong gravity. whether we will see deviations of GR, whether we will see better constraints on GR, that we still don't know yet. But we will have tested gravity at unprecedented accuracy. Looking forward a little more for LISA. LISA would be a great instrument for unstructured environments to a much greater extent. As I said before, with LISA, we'll see mergers of massive black holes. We expect massive black holes to always be accompanied by a disk or some kind of an environment. So therefore, gravitational waves from LISA events or from LISA sources, which especially the ones which we'll see for a long time in LISA, evolving for days or weeks in LISA, will give us very stringent localization of these binaries. The same would happen for really high mass stellar binaries. They will show up on LISA band for a long time, so we'll see many cycles of them. Again, very stringent localization of such sources. And if these kind of events are happening within some kind of a disk or some kind of a environment, we would typically expect them to be associated with electromagnetic bursts as well. So again, the multi-messenger aspect of probing the environments is going to be very promising with LISA. And with all of this together, we'll map the universe a lot more in a lot more detail. So we'll have a lot of sources that are completely invisible with electromagnetic astronomy, black holes especially. And of course, we'll have all the other observatories that will show up in the map in the near future. So with all of these together, we will have built a much more refined cosmological timeline within the next decade or so. With that, I thank you for your attention, and I'm happy to answer any questions.
Very much for very nice talk. So please, questions, let's start with the students available.
Could you go back to the map for the asymmetry and not asymmetry model? It was like shaded on both sides. Right. Yes. And so, can you remind me about what the shading entails? Like what's the difference between the lighter shading and the darker shading?
Right. So when you're using a model, you are parameterizing the model with, let's say, the spin parameters over here. So what the code does, the data analysis algorithms do, is that it samples over the entire parameter range of that spin to produce what's the quality of the fit with the data, how well does it fit the data. So this shading quantifies the quality of the fit.
Okay, so my follow-up question to that is is there a reason why your model seems to prefer the 30 to 60% range, or is that kind of like an up in the air question?
So I should say, are you talking about this one? So this is
yes,
not 30 to 60. Yeah, this is not 30 to 60%. The darkest color, yes, the darkest color corresponds to 95%, something called confidence interval. And then the next darker color would be 90%, and then so on. So that's a great question. We have made a model of the asymmetry in the dominant mode of the gravitational waves. What that means is that when you take the gravitational waves, you can decompose it on some kind of spherical harmonics. So it's like a basis, just the way you decompose a vector in the x, y, and z component. And you would decompose a spherical wave in a spherical harmonic basis. And in that, for gravitational waves, as I mentioned before, you have a time varying mass particle moment. That's a bare minimum. But more often than not, you have also higher multipoles, like octopole, etc., etc. So in every modeling that we do for any kind of gravitational wave source, our first target is the particle, because that's always the dominant. And this model only accounts for the dominant mode asymmetry. As you keep adding the higher multiple asymmetry, you will start to see more improvements in the next.
Yeah, I have a very simple question. Could you get back to maybe the first slide of your talk where you elucidated this 1 over r squared dependence for electromagnetic waves? Yes. And the signal strength falls out as 1 over r. Now for electromagnetic waves, this 1 over r squared dependence is actually Well, pretty much necessary because you see a conservation of energy. If you draw a large sphere around your antenna that's emitting the radiation, its area goes as r squared, signal strength goes as 1 over r squared, the energy per time flowing through the area is constant. No energy is lost, nothing is gained. Now, if one were to ascribe that same energy flux to a gravitational wave, if the signal strength falls off as 1 over r, but the area around your emitting object that emits the gravitational waves just is r squared, how does that figure into energy conservation?
So I think the main difference comes in what you're measuring the gravitational wave. You're not measuring the energy actually, you're measuring the strain it's producing on the metric of the space-time.
Yeah.
Right. So you're measuring a different quantity than what you're measuring in case of electromagnetic waves.
Yeah. That's clear, but can one associate some kind of, pointing vector then with gravitational waves? And how does it?
How does the conservation of that work? But yeah, of course you can always associate an energy with gravitational waves as well. Yeah, I'm not sure about that. I have to think about it again.
All right. On the particular range,
Yeah, so your model, you consider the black holes with spins pointing against each other and you consider that underneath emission each other.
So completely opposite.
Yes.
Yeah. In fact, that's one of the very interesting configurations that you have. It's called a super peak configuration. So as I said that as you have spin misalignment, this leads to this recoil. And when you have the spins completely in the plane and opposite to each other, that leads to really large recoil velocities. And that's a special system also because when that happens, you have essentially cancelled out this total spin misalignment if they have the exact same spins in the plane, right? So that's equivalent to a binary that effectively has no spin because you don't have anything aligned to the angular momentum. And whatever you have in the plane of the object plane, they have cancelled each other out. So in these systems, precession is entirely suppressed. So you don't see this motion of the orbital plane at all. What you see is that the plane just keeps going back and forth like this, and finally ends with a giant peak going in one direction.
So there's research where you try to model different like cosmological events that would produce gravitational waves. How much of it is trying to create a model to fit existing like gravitational wave data, or versus trying to create a model that would predict like new like shape for the gravitational wave, because cosmological wave that hasn't been experimentally like measured.
By the cosmological event, you mean the other source I spoke about? So this one?
Yeah, whether it's like a single like
Yeah.
black hole or binary black hole, like or like a star merger.
Yeah.
How much of your like research is trying to like fit the like LIGO data, or trying to maybe model something that LIGO hasn't seen yet?
Okay. So this is entirely not something LIGO has seen, right? Because LIGO hasn't seen this yet. So this is based on entirely solving for the gravitational waves. So this system, I did not speak about the other approximation that is used in source modeling, which is the perturbation theory part of it. If you go along this axis, then this axis quantifies what's the difference in the masses of the objects in question. So that other source is the black hole with this really spread out, not very dense cloud around it. So that cloud acts as a perturbation on the main metric. And then you use black hole perturbation theory, which is a whole field of its own, to solve for the gravitational radiation. So that is entirely mathematical solving the equation and then mathematically modeling that. This system is where you are, once again, you're not modeling the LIGO data, it's the other way around. You're modeling NR data, and then your model is basically being used on the LIGO data to extract information about the parameters from the LIGO data.
Later in the presentation, you mentioned that like the mass of your body uniquely determines the frequency, given some distance where you're accounting for the redshift. And you said that was assuming only one possible mass for dark matter candidates. Would it be possible to tweak this to account for different masses of dark matter candidates if you assume there might be multiple particles of dark matter? Could you even begin to like check if there are different particles of dark matter?
Not the analysis that I showed here, because that analysis assumes that there is only one dark matter candidate in the universe.
Okay.
So that's a unique thing that you do. Because if you have multiple dark matter candidates and they are all competing for the black hole spin, in that case, how you have to determine the time scale for each of those candidates in which this cloud can grow. And there's a competition up there. And that is not accounted for at all in this analysis. And I'm not familiar with anybody having done that.
Next question.
Yeah, in terms of the dark matter observability stuff, could you explain again why the signal does not depend on black hole mass? Because I can imagine that, you know, free-fall time scale for different systems may be different, right? So and black hole, dark matter are basically, you know, the horizontals, so the amount of time it feels should be basically determined by the time the free-fall time scale. It just depends on the density of the mass of the system. So
right. So that actually relies on or is determined by, as I said, lack of corruption theory. What you do is that you solve for the Klein-Boltzmann equation for a scalar field, basically. So you're solving for scalar perturbations on top of a curved space. So curve metric is the metric that is normally used in this case. When you solve for that equation, you're solving for the quasi bound states, the frequencies of the bound states that can halt. The way this process operates is that you have the potential, you can plot the effective potential for a black hole, essentially, if you're making the gravitational potential what it looks like. And then, because the field has a certain mass, so you have bound states within that potential. And when you solve for the bound states, the frequency of the bound states, the leading order term in that is the mass of the dark matter candidate. So the leading order contribution to the frequency of the bound state comes from there. And then the frequency of the gravitational wave is just twice of the frequency of the bound state. So for a particular mass of the candidate, you have the same frequency of the bound state, and therefore you have the same frequency of gravitational waves. The only thing that depends on the mass of the black hole is the time scale over which the thing will grow.
because we are basically assuming that it is, you know, rolling around the potential boron.
Yeah.
Okay, so basically there's no time scale because of that, and the only mass of the potential.
Yeah.
Other questions? Please.
Just a terminological issue. Is there a difference between post-Newtonian and Newtonian here? On the slide? What is the difference?
Yes, so in Newtonian theory, you're just doing J over R. But in post-Newtonian, you're actually expanding the 1 over R as a like a Taylor expansion. And then you're counting the higher order terms as you go to higher and higher orders. Then you have more subdominant contribution to it. And then that also, so this is a little further detail than that. That also lets you iteratively calculate the effect of whatever material you have in the space-time, their effect onto the. So in GR, what we have is that mass tells space-time how to curve, and the space-time tells mass how to move. So if you just do Newtonian, then you are only getting the effect of the mass on what the force would look like. But if you do post-Newtonian, then you calculate the first order effect on the geometry due to the mass. Then you allow that to feature into your mass distribution again. and then you calculate the next order contribution to the space-time. So that's what post-Newton means. You're going one step further in the non-linearity of the theory.
The post-Newtonian does mean relativistic. Is that right?
Yes, but it means slow velocities, as I said. So you can't go to really relativistic velocities. So you can't. So when the objects are really far away, the velocities are much smaller than that of light, orders of magnitude smaller than that of light. As they start getting closer and closer, you start to see the full relativistic effects come into play because the velocities can go up to half of c also. So PN does include some relativistic effects, but not everything.
Next session, please. Okay, if this is not the case, let's thank our speaker again.